So magandang araw sa inyo. Today is our last formal meeting. And the announcement that I got is your module quizzes for 7 and 8 will start on the 10th, June 10th. And it might spill over until the 13th. Pero wala akong confirmation doon. Because originally it's 9 to 10. But I think they decided that we make it starting at 10 and maybe until 13. I'm just going to post in the Google Classroom kung ano man yung latest development doon sa module quiz. But it will push through, and I still don't have the schedule for your final exam next week. So ipopost ko na lang din yun sa Google Classroom. Okay? So today we will just discuss nuclear chemistry, and I think the question that you will get from here will be on final exam. Although I have an example here that is similar to the order integrated rate law that I wasn't able to discuss during our last meeting. Okay, so if we talk about the nuclear chemistry, we're talking about the study, okay, of reactions including changes in the atomic nuclei. Okay, so the typical chemical reactions that we have so far, usually it just deals with the electrons. But if we have a nuclear reaction, the one that is involved are all these so-called subatomic particles. But nuclear reaction will only happen if you have a radioactive material. Okay, so all nuclei reactions that we have, usually it involves the fundamental particles like the proton, neutron, electron, and other stuff. Okay, so nuclear chemistry, we could say, is popular in the news. Your news was North Korea. If you have a president there or a leader named Kim, who always make a threat that he will nuke other places. And then in the Philippines, they're trying to revive the nuclear power plant as source of energy. Okay, so if we're going to look at the nuclear chemistry, I think we have to review this thing. So X there is the nuclide or the chemical symbol, okay, or the element symbol, and C there is the atomic number, and A is the mass number. So if you recall, atomic number is just the number of protons. Mass number is the number of protons plus the number of neutrons. Okay. Now, in addition, you also introduce to the different particle unit or fundamental particles or subatomic particles. So you have the proton, which is just the hydrogen. Your atomic number is 1. Your mass number is 1. So that means it's all proton, no neutron. And then you have neutron, wherein you don't have any atomic number, but you have a mass number due to the neutron. And then you also have the electron, which has atomic number that's -1 because it has a negative charge and no mass number. It is what? 1846 lighter than both the neutron and the proton. So you can put it as an electron or the so-called beta particle. Now, if you have a positive electron, it's a beta particle there or an electron that has a positive charge. So you have there the so-called positron. Positron is just what? A combination of positive electron. The words positive electron will give you the positron. And last but not the least of these fundamental particles that we have is the so-called alpha particle, which is just helium. Okay, it has an atomic number equals to 2 and mass number that is equals to 4. Okay, so all of this will be useful, especially when you balance nuclear equations. So one main difference between the chemical equation and the nuclear equation is, in a chemical equation, whatever the element that you have in the reactant, that is also the same element that you have in the product. But that is not true for nuclear equation. They can change from one element to another. Now, in balancing nuclear equation, the only thing that you need to do to take into consideration is you need to make sure that the mass number is the same on both sides. For instance, the reaction here, uranium-235 reacting with neutron, you produce cesium and rubidium and 2 neutron. So if you're going to look at the mass number here, this is the number here. So what you're going to do when you add them together, you have what? 235 plus 1, that's 236. 138, 96, so that's 234 plus 2 times 1, so that's 236. Another thing that you need to consider is it's not only the mass number that are the same on both sides. You also have to take into consideration that the atomic number or atomic or nuclear charge is the same on both sides. So you have the same reaction that we have there. So what happened? So it's the same reaction. So we add all of the atomic charge, or what we call atomic number. So you have 92 on one side, and then 55 plus 37, that's 92. 2 times 0 is 0. So you have the 92 on both sides. So let's try to work on this. What are the X here in the given reaction? Try to do it yourself. So what's the X?
Helium po.
Okay. Is the X helium here? So if we're going to do get here, 208, 212, so that means this is 4. 84, 82, that's 2, so it's helium or an alpha particle. So we could say this is an alpha decay because one of the product is an alpha particle. Now how about the second one here?
Electron.
So you have here 0 because they have the same atomic mass number, and then here 55 and then 56, so that means that should be a negative 1. So it's either an electron or a beta particle. So this is an example of a beta decay. Now the question, what's the main difference between a nuclear reaction and a chemical reaction? So this table summarizes the main difference between the two. So as I've mentioned, okay, if you're dealing with the chemical reaction, you have the same element. So what happened? The atoms are just rearranged by bond formation and bond breaking. Unlike chemical reaction, the nuclear reaction, your elements or isotopes of the same elements can be converted from one to another. So nagbabago yung element doon sa nuclear reaction. Unlike doon sa chemical reaction, kung ano yung reactant mo, yun pa rin yung product mo. Makikita mo yung mga element. Another thing that I have mentioned already, only electrons participate in a chemical reaction, specifically the valence electron. Okay? But in a nuclear reaction, all subatomic particles can participate. So protons, neutrons, and electrons, and other elementary particles may be involved. Okay, so that's another we could say difference between the two. Okay, and then this is I think another difference, and this what makes your nuclear reaction very popular. Okay, your chemical reaction will just give you release or absorb a small relative amount of energy. But the nuclear reaction can absorb or release tremendous amount of energy. That's why it's a good source of energy and unfortunately a good weapon of mass destruction. Okay, so I think that's the way that main difference between the two. You can produce a tremendous amount of energy by just using the nuclear reaction. And last, if the chemical reactions are affected by these different variables and factors, the nuclear reactions, they're not affected. Okay, you can only have a nuclear reactions if there's what we call radioactivity, or if your materials is radioactive, it emits radiation on its own. So let's look at the stability. Okay, how can we say a given element is stable? So they found out that certain items or certain numbers of neutrons and protons are extra stable, especially the number that contains neutrons and protons of 2, 8, 20, 50, 82, and 126. It's just similar to this extra stable number of electrons in the noble gases. So if we're going to look at the stability here, you can take note of the following observations that they have with regards to the subatomic particle and how it affects the stability. Okay, so usually we could say in terms of stability, there's what we call a strong nuclear force that you have there. Okay, so this strong nuclear force, if we're going to look at it, it has something to do with excuse me, the force of attraction that is present over extremely short distance between all nucleons. So when we're talking about nucleons, we're talking about the protons and the neutron. Now, this strong nuclear force is much stronger than the electromagnetic force in short distances. However, the electromagnetic force is more significant over longer distances. So what are these properties of neutrons? Neutrons is the one that dictates here. So neutrons serve as what we call nuclear cement. It glues the neighboring protons together despite what the electric repulsions of the positive charges. But it's only for over short distances. At large distances, the strong nuclear force become less significant. Okay, and what you observe there, the more protons in the nucleus or in the heavier atoms, you also need to have more neutrons to hold them together. Okay, if you observe at heavier atoms, the mass number is more than twice than the atomic number. Because what happened there, for every one proton, you have most likely 1.5 to 2 twice as many neutrons. You don't observe it at the smaller atomic nuclei because what you have there is they almost have the same number of protons and neutrons. Like carbon. Carbon is what? Around 6 proton, 6 neutron for carbon 12. You have fluorine 19, 9 proton, 10 neutron. Okay? And if you have a single neutron, it's usually unstable. Why? Because it will convert, okay, itself to a proton and an electron. So it has its own what we call effects on this so-called stability of the material. Okay? So it says here, nuclei with even numbers of protons and neutrons, they're more stable compared to the odd numbers of neutrons and protons. As I told you, a single neutron, what it do, it will convert itself to a proton and electron. And then all isotopes of the elements with atomic numbers higher than 83 are radioactive. And all isotopes of technetium and promethium are what we call radioactive. And if you're going to look at the number of the stable isotopes, you have more of them if you have even numbers of protons and or neutrons, as seen here. Okay? Now, what does this mean? Okay? So, why do they behave like that? Why are some atoms or nuclei stable? Why are the others are what we call unstable? So you have this so-called belt of stability here in your module. I think they call it the band of stability. So what is this band of stability, belt of stability? In some books, you have zone of stability. So usually it's just a graph that depicts the relationship between the number of neutrons versus the number of protons and the area where there are stable nuclides. Okay? So when your nuclide has 84 or more protons, it tends to be unstable and likely it will undergo radioactive decay. However, if you have lighter nuclides, they are usually stable, and when the C is equals to the N, or you have an N over P ratio that is equals to 1. So this is where you see in your uh, stability, like this one. So you have here 20 and you have what we call 20. So if you're going to look at the 1:1 ratio of the neutron and proton, this is it. But as you could see at heavier molecules, the belt of stability increases. So if the nitrogen to proton ratio is too large, the one that is favored is the beta decay. Okay, that is the one above the band of stability. But if it's below, okay, the neutron protons equals to 1 ratio, the stability, the one that is favored is the positron decay or the electron capture. And I have some reactions for that. So you have what we call an idea about this stability stuff that we have. Okay? So if you're going to look at it, what are these beta decay? So beta decay can be what we call describes as the formation of beta particle. So if you're going to look at this, I could say it's an increase in the proton. That's the main characteristic. Okay? So in a beta decay, you have there a neutron that forms into a proton and a beta particle. Okay? Now, positron decay, on the other hand, what do you have? Instead of a beta particle, you have a positron. That's the positive charged electron. So if you're going to look at what is happening here, so you have a proton forming neutron and a positron. So you could see here, it's just what? The reaction of the different fundamental particles. So meron kang neutron na nagiging proton at electron. Meron kang proton na nagiging neutron at positron. And if you have an electron capture, so you have there an electron that is in the reactant side reacting with a proton to give you a neutron. Okay? You can also have an alpha decay. So the alpha decay, you form an alpha particle. And you can have this spontaneous fission wherein a big element is broken down into a smaller nuclei. Like your californium 252 breaking down to form indium 125 plus 2 neutron. Okay, so the one that I'm going to discuss more to you here with the calculation is the kinetics. Okay, we didn't discuss the integrated rate law. So when we say integrated rate law, this is predicting the concentration of a reactant after a given time, given the reaction. So in the radioactive decay, it follows the first order. So the way that we wrote this in terms of radioactive decay is this one. But in terms of integrated rate law, we use the A at a given T over A initial equals to KT. So as you could see, it's just the same. Okay? The only difference is you use N for the radioactive decay instead of A, the concentration of A. Here, a number of atoms at time T. And instead of K, you use, what's that, the lambda sign? And the half-life is also the same in the first order, that's 0.693 over K. So what we're going to do to prepare you for your module quiz, which can start maybe on Thursday, okay, is to solve problems. So for instance, we have here technetium-99 is used as a radio tracer for many organs. With a half-life of 6 hours, what is the amount of 100 milligram technetium-99 remaining after 2 days? So how are we going to solve this? Okay, so we solve this maybe by what? Getting first the K. Because if you're going to look at this, this is the formula that you're going to do, or you're going to use ln T over N equals to negative alpha T. Am I right? So what is the one being asked? NT or N? Or NO? You have time, but you don't have this. Which one do you have? NT or NO? Anyone? Ano yung meron kayo? NT or NO? Meron kayong NO. But you don't have this one. But you can get it from T. Oh no. Right? Ano yung half-life nyo? So you do it like this. T1 half. And if you have that, that's 0.693 over 6 hours. So what do you have? 0.693 divided by 6. So you have 0.1155 per hour. So we can use that there. So ano pa yung given dito? So Ln, you're asked for NT, and this is equals to what? 100 milligram. And then you have here 0.1155 hours. You multiply it with what? 2 days. For 1 day, you have what? 24 hours, right? So you can put it, if you're going to rearrange them, how are you going to eliminate Ln? So this is NT 100, and this will become E raised to 0.1155 times 48 hours. Because 2 times 24 is 48. Okay? And you can put this like this, 100 times E raised to the 0.1155 times 48. So ano yung makukuha nyo? Anyone?
0.39.
0.39.
39.
39 milligram. Analyze. Kaya?
Sir, sir, yung half-life po na 6 hours, ay, yung half-life po, yung, ano po, yung 0.690 po, ay,
6.0.
constant po yan.
Ay, given yun. Itong 0.693 is has something to do with ln2 over the rate constant T1 half. So ano ba yung value ng ln2? Constant yun 0.693. You get it from ln2. Yung half-life na ano dito, given. Okay? Kaya? Baka may lumabas na ganito, similar sa ganito sa module 7 nyo. Kaya ako inano dito, tawag dito, diniscuss. Now, you can also have a problem like this one, but this is just simple. Iodine 131 has a half-life of 8.1 days. So, determine the rate constant of iodine 131. So, it's just T1 half 0.693 over the rate constant. So, all you need to do, replace nyo yan with T1 half, and then you have 0.693 over 8.1 days. So you will have here per day. Ano yung sagot nyo doon? 0.693 divided by 8.1.
Mm-hmm. 0.086.
Okay, 0.86. So, kaya? So, another thing that we can look at, ano bang uses nitong mga isotopes na to? Mga radioactive isotopes. Well, for one, you can use it for determining the age of a material. If it's biological based, you can use the radiocarbon dating. If it's a much older one, you can use the one using uranium-238. Okay? So radiocarbon dating in archaeology, they try to determine the age of a particular material or artifact. But they can also be used in money-making industry like food. Okay? Especially what? So wine. Ano bang ano nila sa wine? Mas matanda yung wine, mas mahal. So how are you going to make sure that hindi siya peke? So they look at the C14. And based on the C14, they can determine the age of your wine. Okay? Now, before we go with the other uses, I'd just like to clarify to you here the difference between fission and later on fusion. Okay? So, ang definition lang ng dalawa nito is maybe baliktaran sila eh. So, when you have fission, what you do, if you have this so-called nuclear fission. So, if you have a nuclear fission, this is the breaking of a heavier nucleus into two nuclei with small mass number. Okay? So, pag nakita mo dito, you have uranium-235 and then you break it in strontium-90 and xenon-140 and some atomic particle. And it generates energy. And what's the basis of the energy here? Where did you get this thing? This is from what? What do you call this? E equals to mc squared. The ever famous E equals to mc squared. Anyone know what this formula is? That's the theory of relativity by Albert Einstein. So what does it says here? So he said, okay, that the mass defect in a given atom can be a good source of energy. So if you're going to look at this, you just look at the mass defect here of this with this one and multiply it with the speed of light. And that's what you get. 10 to the negative 11 joules from a uranium-235. Or it will generate around 10 to the 13 joules per mole of uranium-235. And that's what? Much, much bigger than the one that you can get from 1 ton of coal. That's the basis that they have of using nuclear energy as a source of energy. Okay, so in a nuclear fission, you can have this what we call self-sustaining sequence, the so-called nuclear chain reaction, and you can what we call divide them as subcritical. When you have a chain reaction, that's where the nuclear fission is self-containing or self-sustaining. So if you have a subcritical chain reaction, so that is where on the average, there's less than 1 neutron that is produced per uranium-235 that is consumed. And if you have a subcritical chain reaction, the fission will eventually stop. Now, if you have a critical chain reaction, there is an average of exactly 1 neutron produced per uranium-235 that's consumed. And this fission can then be self-sustaining at the same level. But if you have a supercritical chain reaction, there is an average of more than 1 neutron that is produced per uranium-235 that is consumed. And this fission can increase its rate rapidly and a violent explosion can result. Okay, so that's the difference of this what we call chain reaction. And the minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction, ang tawag dyan, critical mass. Okay? Now, this has been the basis of this what we call the atomic bomb that you have. The one that they dropped in Hiroshima, Japan, they have their what? Uranium material, U-235. It's equivalent to 15 kilotons of TNT. Okay, the one that they dropped in Nagasaki, okay, it has plutonium. So that's the difference of the two. But both of them are what we call generated from nuclear fission. Kasi meron tayong hydrogen bomb, but the hydrogen bomb is not from fission. It's from the other one, which is the so-called nuclear fusion. Okay, so the nuclear fusion, if one is breaking down a big nuclei to smaller nuclei, the nuclear fusion is the other way around. So if you have a nuclear fusion, this is the combination of two light nuclei into a heavier or more stable nucleus. So example na meron tayo dito, deuterium reacting with deuterium to produce tritium and hydrogen. Deuterium reacting with tritium to give you helium and a neutron. And you have lithium reacting with deuterium, it will give you helium. And each of them generated some energy. At ito yung principle behind doon sa tinatawag nating hydrogen bomb. They uses fusion reaction to destroy a large target area. So yun yung difference nung fusion tsaka fission. Okay? Now, in addition to the radiocarbon dating that I have given you, there are many uses of this, what we call isotopes. If some of you ended up in medicine or becoming a doctor, some of you may utilize this material. Look at the half-life that you have there. Except for this one, all of them are what? Short half-life. Person experience this one. Iodine 131, it lasts for 8 days, or the half-life is 8 days. So my wife used it for her thyroid. And the others are being used in almost all general application in medicine. Okay, so it's a very good, we could say, imaging material. Another application we could say of the radioisotopes. Are you familiar with the Krebs cycle? How do you think the scientists determine, okay, the compound in each of the cycle? So what they do is they use a radiolabeled substance, and they try to trace and monitor what happened to them during each cycle of the Krebs cycle. Okay, I have a first-hand experience of using a radio-labeled one, the safe one. Okay, when you say the safe one, the not so penetrating, yung nakakatakot na radioactive material is the penetrating one because it can hurt your internal organs. But there are radioactive materials that's non-penetrating. So kapag meron kang gamma ray, penetrating yun. Okay? But yung iba, as long as you follow the safety procedure, you'll be fine. The only one that I don't want to use is the P32 because that's a penetrating one. I remember when the radioactive room, somebody's using a P32 from another group. I'm not going to use the room for a week just to make sure until it's decontaminated. Okay? Now, I don't know if you know it, but we are exposed to radiation every year. And we can measure it in terms of RAD or REM. But if you're going to look at the average yearly dosage, at least for the Americans, this is the one that you have. And where's the big source? The X-ray. It's not advisable that you have X-ray. Usually, sabi nga nila, once a year, if possible. Okay? In nuclear waste, it's just what we call low, unless you have a nuclear meltdown, like what happened in Fukushima in 2011. Okay, the Fukushima nuclear power plant was what we call, it's not really destroyed, but it has a meltdown. Why? It's not because of earthquake, but because of the what we call tsunami. The nuclear plant was able to withstand the earthquake, but the tsunami is just too much. And that's the risk that we have if we want a nuclear power plant in our country. Okay? And another way that you need to remember, the problem that they have is the how or where are you going to dispose the nuclear waste? Because those nuclear waste, they will last over multiple lifetime. Okay? So what are the other applications that you have? You can use it in food. So see the difference of the one that is irradiated, the non-irradiated. So it can kill some of these pathogenic bacteria, but the only problem is at higher dosage, it will affect the quality. I have a first-hand experience because my best friend scientist is working in PNRI, a Philippine Nuclear Research Institute there in the Philippines. And one paper that we come out is the treatment of radiation on, are you familiar with Banaba? Lagostremia speciosa, I think that's, I'm not sure if that's the exact scientific name. So what we did, we radiate the leaves and see how it affects some biological property. And we found out that a certain dosage, it gets the maximum activity. Another application I think that I can remember of the nuclear chemistry is when they solved the mango infestation in Guimaras. Okay, so the mango industry was under attack during that time because of the insect. So what they do, they sterilize an insect, and what happened if this sterile insect mate with another insect in the area, it will make that insect sterile. So within that time, they were able to save the mango industry in Guimaras. So that's all that I can talk about the nuclear chemistry. And thank you so much for coming today. This is our last meeting. Unless you want to meet me outside class R to prepare for your, if you have any questions in your quiz and the final exam. Question? Tanong.
Sir, regarding po dun sa half-life po,
Hmm.
may incidents po ba sa mga questions na labas parang whole life? Yung which,
Wala.
yung
Half-life talaga.
i-multiply sa 2.
Or ang gagawin doon, if ever it's not half-life, yung time mismo.
Okay.
Remember, the general equations that you have, kung titingnan natin yung equation, di ba ganito? So itong T na to, hindi naman lagi half-life yan eh. So most likely, lalabas talaga yun kung after how much or after how long. So kung half-life yung lumabas doon, usually, hindi yung T ang kukunin mo. Ano yung kukunin mo? Yung K. Given yung half-life, kukunin mo yung K, tapos gagamitin mo dito. Klaro?
Yes, boss.
Handa na ba kayo? Binigyan ko kayo ng assignment as request ng classmate nyo. Tanong. Huwag mahiya. Ito na yung last meeting natin formally. May tanong?
Sir, tanong po concerning dun sa mga assignment.
Yeah, as I've told you, hindi ko i-required, pero it will be helpful for you if you answer them. And if you submit, should I have what we call, maybe at some points, I have some basis to get where I can get. Wala pa yung final exam schedule, but I will let you know in the Google Classroom once I got to know what it is. We have a meeting after this class. So hindi ko alam kung gising pa ako.
Sir, possible po ba na if ma-submit namin yung assignment early, kung ma-check niyo po, pwede niyo pong
ang gagawin ko,
balik
pag sinubmit niyo yun, i-send ko sa inyo yung answer key. Hindi ko checkan, pero makukuha niyo yung answer key.
Thank you po, sir.
Yun yung ibig kong sabihin doon, pag sinubmit nyo before nung deadline, you will get the answer key. Hindi lang answer key, yung way na pag-solve doon sa problem na yun. Hindi ko ni-required kasi baka may magreklamo eh. So it's up to you. Remember the mantra that we have, chemistry. Because I'm hoping if you do that, and if you encounter the same type of questions doon sa module, you are in a much better position to answer it than meeting that type or what we call encountering that type of questions the first time around during the quiz. One way na rin sa akin makita kung sino talaga yung gumagawa. Because I don't want to make it a requirement because mamaya magreklamo, mahirap na. Tanong.
Wala na po sa akin, sir.
Yung iba,
Wala na rin.
Wala na po, sir.
Wala na po, sir.
so okay na tayo? Last meeting na natin to. So are we good?
Yes po, sir.
Magre-request sana ako sa inyo magpakita at magpa-photo tayo eh. Ewan ko kung komportable kayo. So if not, good luck sa exam ninyo. Maraming salamat for attending the class.